substance which I'm very fond of, water. Maybe most of you probably don't know me. I started working in semiconductors, then I dived into water to try and understand how the structure of species could be described. After that, I came out of water and I headed off in the direction of quantum field mechanics. And as my friend Vitelio said, I then headed off in direction of biology. This is therefore a multidisciplinary story which I'm going to tell you, and it is a story because I'm going to show to you that the things which we think we know, but which we probably should take a closer look at. My story starts with Galileo. Now, Galileo, I'm sure you know of him because he applied the Kepler model. Not many people, in fact, know that one of his first challenges against the church was to explain why ice floats on water. This happened 400 years ago in Florence. And if you're interested, I was in Florence 2 years ago for a meeting. The poster is up here on the screen. And have a look at the name of this Aqua Incognita, that's the title. There were 30 leading world specialists on water at this conference, and these 30 people all agreed on one point: they didn't know what water is. Now, obviously, if you don't know what water is, you can't be surprised if people come up with rather magical properties belonging to it. So there are 2 articles of my own in this book, which you can look at, but there are many, many other fascinating ones as well, and I warmly recommend them to you. Now, as a chemist, when you look at water, well, this is what you think of. In other words, you've got molecules which interact. It's called the van der Waals interaction. And here you've got a graph which really shows you what to expect. Given the molecular weight, the more molecular weight, the higher the boiling point. And as you can see, molecules such as radon with a molecular weight of 224 grams per mole, it turns into a gas. In other words, behaves like a gas. Now, have a look at water here. You can see there's something wrong, or there's something anomalous. You've got the increase in molecular weight, but the water is ridiculously light, but it's still not gas. It's still water, it's still liquid. And this is one of the big mysteries of science. Why is it that such small molecules with such low mass, 18 compared with 228 for radon, why is this molecule appearing as a liquid? There's another thing which is really striking with water. It's the table which you look at below here. This sums up the critical pressures and the critical temperatures of 3 liquids. You've got mercury. You're familiar with this. This is the record man of liquids. It's always liquid, practically all the time. But look at its molar mass, 220 grams per mole. And of course, therefore, it's understandable why it should be liquid. What's in third place here? With its 18 grams per mole, it's in third position. And it can even beat mercury in some conditions. We've also got the critical density, and here you can see the third once again comes in third. It's the third liquid with the biggest state of cohesion, and once again, this is a mystery we should try and explain. Now, chemists say, well, I mean, we'll take the dipolar aspect. We'll say that water has a negative and a positive charge, and we'll say it's a dipolar moment which is interacting here in the water, and this explains everything. Well, we tried this, but we saw the explanation was not satisfactory, so we've introduced, or a concept of hydrogen bonds was introduced. And here, when the hydrogen bond idea was introduced in 1920 by Maurice Higgins, let me remind you that Maurice Higgins was not a Nobel Prize winner. He wasn't a researcher, he was a master's student, and he suggested that hydrogen could combat 2 oxygen molecules, and go back to this idea that hydrogen could be up against 2 hydrogen molecules, bigamous hydrogen. According to Huggins, this was totally impossible as well. Now, what's the situation today? Well, we find a lot of work ongoing, talking about the memory of water. You've got Luc Montagnier, who gives you results, and what do we see in them? Well, lots of people say, no, this doesn't work. You've got Armstrongs, which are still there, and you explain, it's just out of the question. It's not going to work. It doesn't work. So what can we do about this? Well, let's look at the Nobel Prize winners, because they're reliable. Here you've got Linus Pauling, chemistry and peace prize winner, double Nobel Prize winner. He goes back to the hydrogen bonds, and he says that is a fundamental concept. And everybody listens to him, and everybody listens to him so much that you realize that these hydrogen bonds exist in water, but they also exist in the heart of proteins and in the heart of DNA. And there you realize that this big immense relation, this appalling revelation of chemistry, well, it's not as bad as all that, because it allows us to live. But is this why we understand it? Well, no, because I said to you 400 years ago, Galileo didn't understand, and we got together 2 years ago, and we still didn't come up with a possible solution. So what's going on here? Well, we can turn to classical physics. You could come up with all the kinds of electrostatic contortions of this molecule. This is the different kinds of Debye, Keesom, London interactions. What do you see? Well, the interaction energy levels are very, very low, ridiculously low, and they do not justify the energy of 0.33 electron volts, which you see. In other words, this hydrogen bond does not, or it cannot be, electrostatic in nature. You've got Bolashov, another Nobel Prize winner, who came up with the dipolar moment theory. You can calculate the water constant. You get a value of 13, but the experimental value is 80. How do you explain the difference? Now, here we're getting to the limits of what we call classical physics. In other words, we went rooting around in the Maxwell and Newtonian equations. Who are the outstanding people of classical physics? It still doesn't explain everything. So, you know that in the 1920s, at the same time as we were introducing the hydrogen bond theory, we were also developing quantum theory. Now, what does quantum theory say about water? Well, we've got lots of pretty pictures here. You've got a diagram of the molecular orbitals. It looks fantastic. You've got the functions, the probability of presence of electrons. It turns in one direction, it goes round, it makes bubbles. But we find out that water is diamagnetic. In other words, if you have one arrow going up, you've got 10 going the other way. And you can see we end at the highest level, which is the HOMO level, HOMO. You've got these different levels, as you can see, and there's a big gap in the energy level in order to get up to the first level, which is a LUMO level. In other words, we can't see any covalent bonds being formed. So we've still got a problem, because we've applied the real quantum physics theory of Schrödinger, and when you apply this, try and do it, you've got problems. When you do these kinds of experiments, very nice physical experiments, and you try and understand what is the orbital which is involved in the hydrogen bond, there's a rule in physics, an absolute rule. When you want to go and look for electrons, where do you pick them up? Where do you get them? Well, at the highest level, which is occupied, of course. So what's the hydrogen bond doing? Well, it doesn't touch the HOMO. It gets the electrons from underneath that, and this is something that quantum physics does not completely explain. The other thing which we have is that try and work on the quantum approach here. Here we have anisotropy in the electrons. These are very sophisticated physical experiments, but look at the results. What we see is at the lower level on the left, you've got a covalent link, and at the bottom right, you have a van der Waals link. You can see that the hydrogen bond should be a van der Waals bond, but as I said, it's not. So, once again, we're running into a brick wall. You can also see this if you analyze what we call the electron density topology. Now, this is the top level of what you can do in an X-ray diffraction, and we look at the saddle points. These are the points where there's a meeting of electron clouds. Now there are three in a water molecule in the dimer, and you can see number 1 and number 2, which correspond to the OH bond, and you've got point 3, which corresponds with the hydrogen bond. What can you see? That point 3 isn't at all like the other two. The electronic density is positive, the other two are negative. So this means that there are two covalent bonds and there's one van der Waals bond, and you don't see the hydrogen bond. And you can understand now why Mr. Vitellio said to you that we have to turn to electric quantum field theory. Here we've got the quantum field theory looking at the second quantization. The first one doesn't allow us to doesn't allow us to find the solution, but we got the second quantization. What you see here, we're looking at something we've actually neglected. Juan Galileo says that ice floats on water. Did you notice that if that were true, then it's not so dense, but if it's less dense, then it means it's full of vacuum. And maybe the vacuum is what's at the heart of this mystery. Now, what does quantum field theory say? What does it say? Well, it says vacuum is not the right word, because what's empty, the vacuum, it's not actually empty, it's full of what? How can we explain this? If we're looking for energy not outside, if we're looking for energy in the space between the molecules. Now, you say to me, well, the empty means there's nothing, so, I mean, how can you understand this? Well, we've got physical experiments which demonstrate that what is empty is not empty. You've got the Casimir static effect where two plates are attracted and there's nothing between them. You've got the Lamb effect, which demonstrates that the levels of energy must be calculated at the second quantization level in order to understand the variables which are observed. And you've got the Casimir variable effect, which shows that you can transform a virtual object into a real one. Now, so quantum physics field theory opens up a whole new world for us. It's a virtual world compared with the real world. And this is really, I think, what's at the heart of the properties of water. We have something which exists, but we can't see. Now, all this is rather technical. My friend Vitellio is trying to explain what phase coherence is. Now, I'm not going to give you a big long speech, but I could say it's a non-switching of the angle operator compared with an operator in terms of number of particles. I could say it's even simpler than that. Or you can count. Well, either you can count or you can't. And here you've got two films going on. On the left, you've got the Brownian movement, Brownian motion going on. And if the balls are moving around, I can count them. On the right-hand side, it's what we see in the sky. That is to say, clouds, birds. Can we count them? Well, no, we can't, because they keep moving around all the time. But you can see that the envelope which defines that can be defined, and this is the coherence domain. What if water like that? What if what you see on the right is not what you should see on the left? Would that change things? Now, yes, it does. Of course it does change things. And here I'm getting down to the detail, because all this is quite unbelievable. It's been published. There are 3 books published on this. You see them. You've got a macroscopic quantum coherence in which we've got medios and Preparata, and the latest book, Quantum Physics, Realistic Quantum Physics by Preparata. I do admire so much of these two physicians on the screen. They've died. They're no longer with us, but they've left these books. I've read them. They're fascinating. Do read them, and you learn what the vacuum is, what emptiness is. Now, emptiness, vacuum, it's something which is shapeless down at the bottom slide, which is moving. And when you see this, well, I mean, the scale is very, very big here, but a water molecule, its electrons are small enough, are tiny, and they can see these fluctuations in the void and use it. Now, I'm not going to go into all the details of these coherence equations. The idea is simple. Instead of exciting the molecules with an external beam, we'll use a virtual particle to excite them. In other words, using energy, virtual energy, to excite the water molecule. And then all people who work in spectroscopy, you know that once you've excited the molecule, then the energy has to be relaxed. Where will the energy go? Well, yes, of course, it could go back to its fundamental state, and this is what we usually suppose. But the idea of coherence is it could relax in a different fashion. It could send its energy to another neighboring molecule, and then that neighboring molecule could use that and pass it on. You can transform all this into equations. Here they are. To calculate this, we need to look at the spectrum of the water molecule in an excited state, and you can see the spectrum here. Now, this always makes me laugh when people say, well, H2O is just so simple. Do you think this spectrum is simple? Have a look at it. Have a good look at it. That's the way in which a water molecule reacts when you send a photon into it. See how complicated it is. So water is a very, very complicated matter. So you're excited and it responds with these different levels of energy, and you can do the calculations with this coupling here. Depends on the level of excitation, and this gives us what we call the oscillation and transition force, and you translate this into the coherence equations. Here we are. Here's the result. In other words, each electronic transition of the water molecule has been studied. This was published in 2012, so you can read the article if you wish, and you'll see that every time we can associate a domain of coherence, that is to say a strong association between the electromagnetic radiation which has excited the molecule and what we call the phase, which is fixed here. It's phi, and this is fixed at a specific level, as you can see. Now, what's remarkable is you've got critical densities of condensation, and I'm talking about macroscopic quantum physics here, macroscopic, and you can see that you've got a level highlighted in red, which the interpreter can't see, but this level creates a coherence of 0.16 electron volts. Now, this is exactly what we've expected to see. The picture you see here is a picture of a hydrogen bond fluctuating. Now, this is because in the background there's a field, and the field you have bottom left. In other words, you have a kind of conglomerate of radiation and matter together, which is really water. Now, look at the frequency which we foresee for the electromagnetic field. We're talking about the same sizes roughly. For physics, you would say, well, this is ordinary. You're just describing a quasi-particle with the mass and is generating the coherence, which is up on the screen. Well, that's a boson in physics. A boson can condensate. That is to say, it can give a condensate of Bose-Einstein, and if you will come up at the end of the equation with 270 Kelvin. In other words, liquid water could be a condensate of Bose-Einstein at a high critical temperature, and that changed everything. When you've got this kind of Bose-Einstein condensate, it's not an ordinary liquid. It's a liquid. You can have this kind of image. These are dipolar moments which are aligned, which remain aligned with the same phase. And what happens when I put another solution in this, as Professor Montagnier will explain? Well, you remove matter. Well, of course, but if you remember this coherence, has this coherence been removed? Well, physics will say yes, if we're above the critical temperature of the condensate. But what if I'm below that temperature? Well, it remains. It stays. In other words, you can get information even if the material object is no longer there. And this is something which, we had a Nobel Physics Prize winner who talked about this. This is just what I'm saying as well. We've got the symmetric Lagrangian and the asymmetric ground state. And all physicists know that when you've got this situation, then you have an emission of Namber-Goldstein bosons, and these Namber-Goldstein bosons, we call them hydrogen bonds. But these are vector bosons which pass on, vectorize the interaction. This is a Bose-Einstein condensate, and these boson vectors are Namber-Goldstein bosons. So the picture of this here is very different from what you usually find in biology books. Two kinds of water. When you increase the temperature, then you keep a part of the coherence domain, and the other part starts to go into fusion, and you've got incoherent water, which is in variable proportion depending on the temperature. Here we move on to the link with the next presentation. Luc Montagnier is going to show you outstanding, fabulous experiments which really lead to scientists' jaws dropping. But now, I'm not saying I'm right, but just imagine that water is a Bose-Einstein condensate with a relatively high condensation temperature. If I've got coherence domains, if I don't have coherence domains, now, if you know how the memory of a computer works, you've got the ferromagnetism. That's to say, you've got domains which are ferromagnetic, everything is aligned, and other domains where they're not aligned, and these are non-ferromagnetic. When you write on your USB key or on your memory, what you're doing, if you want to put a 1 for information, then you line up the moments in the ferromagnetic moment, but to do 0, you remove that alignment. Could you do that with water? Couldn't you have a 1 byte for coherence and 0 bytes when I don't have coherence? Since we know the number of coherence domains for 18 milligrams of water, here you've got the figures. If I can code 1 byte for one domain of code, I've got 1 byte for 18 grams, I've got 1 petabyte of memory. 1 petabyte of memory. And if I go up to 18 liters, I would 1 hexabyte. Here you've got the levels of circulation of information over internet. All books in the world are equivalent to 3.6 liters of water, just so that you can understand how much memory you can have. Once again, taking all the books in the world, 200 petabytes. It would take 3.6 liter of water in order to store all the books in the world. If you want to store the DNA of the whole, all the people in the world, 6 billion people in the world, 108 liters of water required to memorize all that. Do you understand what I'm talking about? The biology of tomorrow. We're talking about heavyweight physics. We're not talking about some little experiment. It would be time. The time is right to take all this into account, I think. Now, people say, well, you need experimental proof of this. Where are all these domains of coherence? I want to see them. It's not easy, because if you're talking about Einstein and condensate, they are non-observable, because we're talking about quantum phases here. But here you've got a spectrum with 4 phases. Now, when I looked at this, I just didn't believe it. In liquid water, usually in liquid water, you can identify all the resonances of the different kinds of waves. Look what I can do in chemistry. I can introduce nanocavities which encapsulate water molecules, and they're very nice nanocavities. They're very complicated, coordinated structures, but they're hollow, so let's look at what's inside them. Here we've got 2 types of water. You've got the water on the right-hand side, which makes incoherent water nanodrops. There's no hydrogen bonds, which are made very clearly. But have a look at the aggregate, which is showing on the left-hand side. When I looked at that, I just didn't believe it. This is a triple structure based on a Platon structure. And now water is behaving coherently. You've got the coherence on the left, incoherence on the right, and you can isolate this in a solid form. I'm getting to the end of my presentation, and in the last 5 minutes, let me just move on to the biological side of all this. We know in these fields of coherence, strange things can happen. And physicists are aware of this, are aware of super currents, but the current that we use to excite the water, 2.6 electron volts. In other words, it doesn't take very much to get the electrons out of the coherent water. And once you've removed the electrons, then become free, and they circulate as in a current. But this current is a super current, and you have to see this type of water as something which is constantly moving, never stops, because we're below the critical temperature. You can do the calculations, and now you understand why water is sensitive to electromagnetic fields, because it's interacting with the currents. Just imagine this. You have one coherence domain at the top, one lipidic membrane, and another coherence domain at the bottom. Now, if this was a Bose-Einstein condensate, well, you've got a Josephson junction which appears, and what do you do with these? Well, you can do absolutely fabulous things. You've got lots of them in your brain. This is what Mr. Vitiello was explaining. You've got lots in your brain, in your cells. Look too at when you've got ions. When you have magnetic fields, these ions move. They don't behave like or the way ions usually do. This is my definition of life. People say to me, what is life? Well, looking at everything I've been able to explain to you, I think it's very easy. You transform the number of the mass into the number of objects, and you, above all, we're talking about basically water and ions. These are the major constituents of cells. 99% mole in a cellule, but if the water is a Bose-Einstein agglomerate, then you'll understand what the consequences of this are for biologists. What I like particularly in this approach is now we know what a hydrogen bond is. We know what virtual photons are. You take a magnet with iron filings on it, and you see the lines of fields. You see the virtual photons. We've got the Coulomb's law, which appears electric force, which is the square of the distance. And you've got the Heisenberg uncertainty law. Now here's the covalent bond. It's two levels of energy which have in common an electron. You've got the van der Waals bond as well, these two molecules of water which relax, and you've got the hydrogen bond. You've got the two molecules which do not ignore each other. And here you've got all the links of chemistry, all the bonds in chemistry, which are explained in the same mathematical formality. I've got to the end of my presentation. Let me pay tribute to people who are no longer with us. Of course, William Arthur Ward, very well-known gentleman, who left behind this very nice sentence, which shows that science is a question of reflection. When you've got all the equations I've shown you, then, I mean, these equations represent hours and hours and hours of work. But don't forget, the scientist also works with his heart. We do our job because we are absolutely convinced, persuaded of what we do. We work with passion, and whether it be Emilio Del Giudice, Jack Benveniste, or Giuliano Preparata, I can tell you that all these people worked with passion and with their mind. So I would like to ask all the public here, if you don't agree, then try and listen not just with your mind, but with your heart, and maybe you will get closer to the equations, and maybe will not be quite so aggressive in the questions you might have when you come to questions about this new paradigm. And finally, I'd like to say a very big thank you to Luc Montagnier I have immense admiration for him for his fight to take over the work of Jacques Benveniste, and he really has carried out experiments that Jacques Benveniste would not have thought of himself. And I think that this is why and how we must go beyond Jacques Benveniste. His contribution was immense, but I think we're actually going further than what he did, and we should look firmly towards the future and not towards the past. I've also got you up on the screen a small slide which shows you all the trouble we go to, and people say, why are you doing all this? Why are you going to so much bother? Yes, but we've got experts, we've got people who send us reports in very sententious forms condemning us. I think that the editors of scientific journals should shoulder the responsibility and understand that we should be able to publish ideas which may be revolutionary, but which are not necessarily part of current thought. We're talking about the ideas of the 21st century, not of the 19th.